Hi, Don. It's Mr. Simple here with the Geometry Fall 2020 Practice Final video. So the setup here is that I'll go through a list of questions that will be on the final exam, and then this will show you how then to set up and how to solve the problems that are on the practice final. So the problems that you see me doing here will not be the same problems that you have on your practice final, but question for question, number one, number two, number three, they will all match up and will be the same type of question. So that way you have an idea of how to set it up and how to solve it. So let's go ahead and get started. Number one says points A, B, and C are collinear. Co means with. So when we see collinear, what that means is that they're on the same line. This just means points on the same line. On the same line. And you notice they don't give you a diagram. Like if you kind of peek forward to numbers 2 and 3, you see how they give you a diagram. Number one, they don't. So that's okay. We can make our own diagram. So I'm just going to draw a little number line here, or a segment rather. And so it says BC. So I'm guessing I have some points on here. It doesn't matter exactly where I put it. It doesn't have to be to any sort of scale. So I've got A, B, and C. It tells me BC is equal to 21. Tells me AB is equal to 17, and then it wants me to find AC. Well, AC is going to be this entire distance here. So the entire distance from A to C is just going to be the sum of these two things, 17 plus 21, which is going to be 38. And I should note the answer, the letter choice that has the red asterisk next to it for all of the problems, that is the correct answer. So that way that you know that you're able to kind of check your answer along with me. So number two is the same idea, except here what they have is that they have the diagram already drawn for me. Well, so all I need to do is that I don't know what this is. They have a question mark. I also could call it X if I wanted to. Really, it's just the difference between 31 and 16. So I'm just going to take the difference between 31 and 16, and I would encourage you on all of these things, even if it's something you feel like you can do in your head, just to make sure that you don't make any silly little mistakes. Let's go ahead and just put that into a calculator anyway. So 31 minus 16, which is 15. If you would like to set it up as an equation, you could have said x plus 16 is equal to 31. And then when we subtract 16 from both sides, you get x equals 15. So if it's helpful for you to see it that way, you could have worked it out that way. Otherwise, you just subtract the distance between the two. Number three is similar type of problem, and the only difference here is now we have x's, we have variables in there. But it's still the same idea, which is that the two parts, and this is true for all three of these problems, is that the part, maybe we could say that, because technically what this is a line segment. So let's say the segment, segment plus segment equals the total, right? Or the part, I was going to write the part plus part equals the whole or the total. So all we have to do is just set this up. So I'm going to set this up as 6x minus 8 plus 4, because those are my two parts, my two segments. And that's going to be equal to the total thing, which is equal to 5x. Now, anytime I solve an equation, I just got to get all my variables on the same side. If I have x's on different sides, I want to move everything over to the same side. It doesn't matter if I move everything to the left or to the right. So maybe for this one, I'll move everything over to the right. Doesn't really make a difference here. Negative 8 plus 4, which would be negative 4. And then divide both sides by negative 1. And so we get x equals 4, which is our answer right there. Let's take a look at number 4. Number 4 deals with looking at types of angles and different names that we have for angles. So for instance, on this one, we should define a couple things. So first of all, probably the easiest one, and probably the one that you would identify the most quickly, would be the right angle, right? So this would be a right angle, and this is when it's equal to 90 degrees. Two other types of angles. If you have an angle that is less than 90, that's smaller than 90, then we say that that's because it's small. If you think small, think acute. If I made this a 90-degree angle, that would be 90. But you notice that this is less than 90. So if it's less than 90, we call that acute. So acute is equal to less than 90 degrees. So I'll just write less than 90 degrees. And then if you have an angle, this is also, again, if I wanted to make this a 90-degree angle, I could. And then I could see that this would be, if that's 90, but then this is less than 90, so this would also be an acute angle. And then if I have an angle that is greater than 90 degrees, which this is, right? So because this is greater than 90 degrees, so then we call that obtuse. And so we were looking for an obtuse angle in this situation, so that would be our obtuse. Straight angle is the name might imply, right? So these are all, this would be a right angle, this would be obtuse, right? This would be obtuse. This would be smaller than 90, that would be acute. And then so, as the name suggests, we say straight angle because it's on a straight line. And then a straight angle is going to be equal to 180 degrees, and we'll get into that a little bit more. But basically, the idea is that you know that in a circle, you have 360 degrees in a circle. Well, what if you took half of a circle? Well, half of a circle would be 180, and that's what we have right there. So we're going to use these relationships then to solve for different types of problems. And so on number 6, they tell us measure of angle SKL is equal to 48 degrees. Well, SKL, how do I know what SKL is? Well, we use 3 letters to identify, and the middle letter is the vertex. So this middle letter right here is going to be our vertex. The vertex is the turning point of the angle. Turning point. What I mean by turning point is that if I follow the order here, SKL, so S comes in, here's K, and then it goes back out to L. So it's going in, and then it turns and it comes back out. So SKL would be this angle right here. So we're saying that this would be equal to 48 degrees. And then JKS, so I'm going to just follow it in order, J, K, and then S. So JKS would be equal to 44 degrees. So this angle here would be 44 degrees. And so what this does is that this then, we thought maybe that looked like it was a 90-degree angle, but we can never go off by just what the diagram says. So what we want to do is just find the measure of angle JKL. Well, JKL is this whole thing, JKL. So I just need to add those two numbers together. So if I took 44, I'm just going to take 44 plus 48. Let's throw that in the calculator. So 44 plus 48, 92. 92 degrees. And again, the red asterisk indicates the correct answer. But I'm kind of pretending that that's not there for a second. I want to solve it on my own first, and then see if my answer is there, which in that case it was. So this would have been an obtuse angle, right? Greater than 90 degrees. So this is an obtuse angle, at least JKL, the whole thing. So these two acute angles made up the obtuse angle. Number 7, similar type of situation. We just got to fill in the angles and then see what they're asking for here. So it says EFG is 154. So I just have to follow along with the letters here. So EFG, so E, F, and then G. So that's actually the whole angle. EFG is this whole thing right here. So they're saying that this is equal to 154. And then they're telling me that UFG is equal to 104. So UFG. So then it's this inside angle here that's 104. And then we're looking for EFU. So EFU, this is what we're looking for, the measure of EFU. Well, EFU would be this angle, EF and then U. So this is the angle that we're looking for right here. Well, if 154 is the whole thing, then we just need to subtract, right? So we just need to say 154 minus 104, and that'll tell us this little part right here, which I subtract the difference there, I get 50 degrees. So our answer here would be 50, and then we'll just go ahead and indicate that, 50 degrees. All right, so the same type of thing here, we might have to apply what we're doing, but then it might be in the form of an equation where actually these were just numbers, right? I just had to add the two numbers, subtract the two numbers. Here you see x's, and so I'm probably it's going to be the same thing. I'm just going to have to figure out what x is equal to. But let's start by labeling it, right? And that's always the first part on this, is that you want to annotate the problem so that you make sure. Don't try to just do all this in your head, right? So you want to annotate it. You want to label the diagram. EDC. So ED and then C is equal to 11x plus 9. Well, EDC is this whole thing, so it looks like they're giving us the total, 11x plus 9. And then YDC is 72. So YDC is 72. So YDC would be YDC. So this is 72 degrees. And then EDY is 5x minus 9. So that part right there would be 5x minus 9. Well, we said a moment ago that it's the two parts make up the whole. So here's your two parts. 72 is a part, 5x minus 9 is a part, and then that will make up the whole. So what we need to do is just add the two parts together, which would be 5x minus 9 plus 72 equals 11x plus 9, because the two parts add up to the whole, right? So this is, again, think of this as a part, and this is the whole. Well, so, flashback to Algebra 1 here. We just need to get combine some like terms and get all of our variables on the same side. So let's combine those like terms first. So I see 72 minus 9. Again, even on something simple like this where I could do this in my head, just because I don't trust myself, and maybe because I woke up 5 minutes ago and maybe my brain's not working yet, let's just put that in the calculator anyways. So 63. So 5x plus 63 equals 11x plus 9. Let's get all of our x's together. So this would be a negative 6x plus 63 equals 9. Subtract 63 from both sides. The negative 6x. So we'll do 9 minus 63, which is a negative 54. Divide both sides by negative 6. And we get x equals 9. Now you notice that 9 is not the answer. If I look over here, I don't see 9 as the answer. Well, it's because what they're asking for is they're asking for EDY. Well, what is EDY? Oh, okay, so EDY is this. Right? EDY is this angle, which was the 5x minus 9. So all that means is that we just got to take 5x minus 9, and then we just have to substitute in the x. So we'll take x and we'll substitute it in right there. So I've got 5 times 9, which is 45. 45 minus 9, which is 36. So sometimes they want you just to solve for x, and then sometimes you got to plug it back in to actually figure out what the angle measure was. So in this case, we had to plug that back in. All right, so that is numbers 6 through 8. Next section deals with area. Let's scroll down, see what that next section is. All right, so next section deals with area. Area is not the distance around something, that's the perimeter. What we're looking for here is the area, which is what would it take to fill something, the amount of space inside of something. So a couple things, maybe just kind of make some notes over here. We know that a rectangle is just the base times the height. And then so we can use that relationship then to figure out a couple of these other ones. If I took a rectangle, right, this is a rectangle, and so the area of a rectangle is base times height. And then, but if I took a rectangle, and then I cut it in half this way, notice what shape I make. I don't know if I would have drawn that right, but close enough. So notice what happens is if I cut this in half, I'll maybe try to cut that in half a little better. There we go. Notice what happens when I cut that in half. I get a triangle. So if a rectangle is base times height, and then I'm just cutting this in half, well, then the formula for a triangle is going to be base times height divided by 2. It's because I'm just cutting the rectangle in half. So important thing to realize here is that the height is never the slanted number, right? So you see this 48 that's on kind of the slanted part. The height is never the slanted number. It's always the number that is perpendicular to the base. So this would be the base, and then this would be the height. Those two numbers. Never the slanted part. So then this would be base, which is 65, times height, which is 37.3. And then that's all divided by 2. Again, just use your calculator for this. So 65 times 37.3. Anytime you're working with a fraction and you're typing this into a calculator, hit enter on the top part of the fraction, get that number, and then do divided by 2. Your calculator could screw up the order of operations if you enter in that all at once or if you don't use parentheses. And then so our answer there would be 1,212.25 meters squared. All right, what about this one? Well, this is a parallelogram. So a parallelogram, we can still use the same, looks like a rectangle. I call a parallelogram a leaning rectangle. So all that a parallelogram is just a rectangle that's just leaning over to one side. But it still has 4 sides, and it still has the shape of a rectangle. It's just that the angles aren't 90 degrees. But what still remains the same idea is that if it's base times height for a rectangle, and a parallelogram is just a leaning rectangle, then it would still be the same thing, which is just base times height. So now all I have to do is just figure out what the base is. Well, base here would be 8.7, and I don't need those same numbers twice, even though they gave it to me. You'll notice they're going to give you some extra numbers here that we don't need. Height is never the leaning number, and then the height is perpendicular to the base. So then what I would be multiplying here is just these two numbers. Here's my base, and then here's my height. So then I would have base, which is 8.7, times height, which is 5. And then we're just going to multiply those two numbers together. Again, use your calculator. 8.7 times 5. I got that in wrong. That's always something that calculators have to be careful. You have to make sure you type it in correctly. 43.5 feet squared. Those are our units. 45.3 squared units. All right, what's this over here? So this is a different shape. This is a trapezoid. A trapezoid's kind of like, if you kind of used your imagination here a little bit, trapezoid is kind of like half a parallelogram. Because like, let's say I extended that. Right now I have a parallelogram, right? It looks kind of like that shape there on number 10. So we're going to use kind of the same idea that we did for the rectangle to get the area for the triangle, is that a triangle is half a rectangle. And so we did base times height divided by 2. If a trapezoid is half of a parallelogram, then we're going to kind of use that same idea. And so the formula for this, for a trapezoid, and you have all of these in your toolkit, by the way. So all of these formulas in your toolkit. So these aren't, though it's good if you kind of commit some of this to memory. Again, it's not necessary because all of these are in your toolkit. So for a trapezoid, which will look something like this, the area is going to be the height times base 1 plus base 2 divided by 2. And because we said the divided by 2 because it's half of a parallelogram. And then you're wondering, well, why are there 2 bases? Well, because for a parallelogram, notice that like on number 10, the top and bottom are the same, 8.7, 8.7. But notice here for a trapezoid, the top and bottom are not the same. So we have to account for that. And so that's why there's 2 different measurements there for the base. All right, so we're just going to fill this in. So the height here would be 6.1. Here's your height. So 6.1. It doesn't matter what I call base 1 and base 2. It'd be the same thing either way. 4.9 plus 12.9. And then that's all divided by 2. Again, just throw all this in your calculator. You don't have to do this by hand. Remember your order of operations. Do what's inside the parentheses first. So I'm going to do 4.9 plus 12.9. And then I'm going to multiply by 6.1. And then notice I'm hitting enter each time. And then I'm going to do divided by 2. And so then we get 54.29. 54.29 yards squared. All right, so let's move on to the next page. 9. Okay, so we still have 2 other area problems to do. Let's see, that's 9 through 13. So 2 other area problems to do here. So this is a parallelogram. So we know parallelogram is going to be base times height. And notice what we're given here is that we're given the height and we're given the area, but we're not given the base. So we don't know what the base is equal to. Okay, well, we just got to fill this into our formula for parallelogram. So if area is 1428, I'm just going to fill this in. If area equals base times height, then my area, I'm not going to write A because I know what the area is. It is 1428 equals the base, which is, well, I don't know what it is. That's what I'm trying to figure out. And then times the height, which is 34. Well, remember, anytime you want to solve for a variable, you just do the opposite operation to undo it. So this says b times 34. So the opposite of multiplying by 34 would be to divide by 34. So I've got 1428 divided by 34. We'll get 42. 42 yards. 42 yards. Number 13 is a similar one where we've got just a missing number. So this is a trapezoid. So again, we're going to use our formula for trapezoid, which was the height times base 1 plus base 2, all divided by 2. So let's see what they give us. Let's say this is my base 1, this is my base 2. I don't know what the height is. So height is question mark. I don't know what the height is. And then they do give us the area. The area is 96.8. Well, let's just fill this in. A is 96.8. H is, we don't know. Base 1, 5.6. Plus base 2, which is 12. And that's all divided by 2. Well, anytime you have a fraction, you don't want it to be a fraction. We call this our fraction buster. Multiply by the denominator. So in this case, the denominator is 2. So I'm going to multiply by 2. The reason why I'm doing that is because these two things cancel each other out. And now I don't have a fraction anymore. So I'm going to do 96.8 times 2. I get 193.6. 193.6 equals H. And then let's combine these. Remember our order of operations. Let's do what's in parentheses. So let's do 12 plus 5.6, which would be 17.6. And then now we're in a situation similar to what we were in the last problem, which is that we just need to solve for the variable. So the opposite of multiplying by 17.6 would be to divide by 17.6. And then so we get H equals, and again, we'll throw this in the calculator, 193.6 divided by 17.6, and we get 11. 11 yards. There's our answer. Number 14, next section, deals with transformations. So a transformation is just the movement or the change in a shape. We have a couple different things we could do to a shape. We can slide it, we can reflect it, which is to flip. We can rotate it, which is to turn. We can dilate it, which means to change the size of it, either enlarge it or reduce it. And so that's what the next little section we'll look at here. So starting with number 14, we're looking at a translation. So to translate is just to slide. And again, all these definitions are in your toolkit. So make sure as you're doing the review, make sure you're following along with this in the toolkit. And the order of the review and the order of the final is the same order as that we covered them through the semester. So that way you could follow from Unit 1 to Unit 2, Unit 3, and so on. All right, so this is all what we want to do. How do we know which one is the new one and is the old one? Well, the one that has the letters J, K, L, and I without a little tally mark there, so that's the old one. We also call that the pre-image. And then the new one, which we also call that the image. And then what I'm doing, and how do I know that? Because I look for the prime notation. So the little mark here, we call that prime notation. And what that does is it just shows us how many times a shape has been changed. So a little tally mark of 1 means that it's been changed once. If I just see this, then that means just one change. But if I see this, that means that there's been 2 changes. And then if I see this, that means there's been 3 changes. So, and then so on, right? So it just tells us how many times the shape has been changed. So this tells us this is the original. This tells us that it's been changed 1 time. How has it been changed? Well, it says it's been translated, which is just a slide. So I'm just going to count. It doesn't matter what letter I pick with or start with. I don't know. I'm going to just look at I, for instance. So I want to count from what we call I prime, from I to I prime. Well, let's see. This would be over left 1 and then up 1, 2, 3, 4. So this goes left 1 and then it goes up 1, 2, 3, 4. So left 1 and up 4. Now I need to translate this. We write this. This is in English. I need to translate this into Mathlish. So you know that the x value is your left and right? So if I say x and y, so you know the x value is left and right, and the y value is up and down. So if I'm going to the left, that's a negative. If I'm going to the right, it's a positive. And then if I'm going down, it's a negative. And if I'm going up, it's a positive. So if I'm going left 1, that would be x minus 1. So it's not that. And then if I'm going up 4, that would be y plus 4. Well, y plus 4 would be this. So this one right there, C, would tell me left 1 and then up 4. Another type of movement that we can do to a shape is a reflection. So a reflection, another word for reflection, is a flip. So reflection is a flip. Now we have to identify where did it get flipped over. So if it got flipped over, let's say, for instance, the x-axis, then I would expect this shape to be, and I'm just going to kind of roughly draw this. If it was a reflection over the x, it would look like this. If it was a reflection over the y, right, this would be reflection over x. If it was a reflection over y, if I flipped it over this way, then it would look like this. 1, 2, 3, 1, 2, 3. And again, I'm just kind of roughly drawing this. So if it was, this would be over flipping it over the y-axis. But you notice this one, it's flipped. Well, it's flipped a little bit differently here. So what happens here is that if I took, it almost seems like there's a diagonal line that's coming through here. So if I took a diagonal line that comes through here, and then I flipped the shape over that, so if I went from here to here, that would be a flip over that diagonal line there. And then so that would be the diagonal line is y equals negative x. If it was a diagonal line going this direction, so let's say we had a graph and it was going, the diagonal line was going uphill, right? Let's say that diagonal line was going uphill, that would be y equals x. But it's going downhill, so that would be y equals negative x. This is our line of symmetry, by the way, right? So we're talking about what we're flipping it over. So in this case, we're flipping it over. Our line of symmetry would be y equals negative x. All right, number 16. So number 16 is we're looking at something happened here, and we're trying to figure out what happened. Well, this was a reflection. Notice this got flipped. Here's my old, here's my new. And they also make it easy for me on CUDA because the old is in black and then the new one is in blue. But also look for the prime notation. So look at how where it's flipped. It's flipped this way, and that's being flipped over the y-axis. So we would say that's a reflection across the y-axis. If I take a look at how this is flipped, again, here's old, here's new. And then if I look at how this is flipped, it's flipped this way. So if it's flipped that way, that would be a reflection across the x-axis. All right, let's scroll down a little bit and look at number 18. Our last movement here is going to be a rotation. So a rotation is a turn. So we have a translation, which is a slide, a reflection, which is a flip, and then a rotation, which is a turn. So this would be a rotation is a turn. So rotation is a turn. And then so we just have to figure out how many times did it get turned and in which direction did it get turned. So a couple of things is if I'm going this way, if I'm turning something this direction, then this would be the direction of the clock. So we would call that clockwise. If I'm turning something this direction, which is opposite of the clock, then this would be counterclockwise if I'm going this way, counterclockwise. We know there's 360 degrees in a circle, right? If I made this whole thing a circle, then we know, I'm just going to circle this whole thing for fun. And not an exact circle, by the way, right? But we know the whole thing would be 360 degrees. So each, the graph is split into fours here. So each turn would be a turn of 90 degrees, right? This is 90 degrees, this is 90 degrees, 90 degrees, and 90, which adds up to a total of 360. So we're trying to figure out, well, how many times did something get turned and in which direction did it get turned? Well, so if I look at what happened here, this was turned from here. This is my old, and this is my new. And it looks like it was turned one direction here, right? It was made, there was one turn that was made, and it was made counterclockwise. So this was not a reflection, so it's not A, and that's not D. So rotation of 90 degrees. Why is it not a rotation of 180? Well, the rotation of 180 would have been two turns. And so two turns, one turn would have been here, and then a second turn, you would have ended up here, right? You would have ended up with something like that. So that would have been two turns, but we just did one turn. All right, let's look at 19. So with 19, it looks like there was definitely a turn here. This wasn't a flip. So I know for sure that it's not a reflection, and I know it's not a translation because it wasn't slid. And then we have to see how many times was it turned. Well, if it was just turned one time in either direction, either one turn here or one turn here, it would be either in the quadrants, by the way, we call that the first quadrant, second quadrant, third quadrant, and then fourth quadrant. So one turn would have put us either in the first or third, but the fact that we ended up here in the second turn, or I'm sorry, the second quadrant, that means there was two turns. And you'll notice that it was actually two turns in either direction. So it could have been 1, 2, or it could have been 1 and then 2. So 180 is the same, counterclockwise and clockwise. So 180 clockwise is equal to 180 degrees counterclockwise. So whether that's at, so you notice that way it just 180. So it just says 180. All right, so let's scroll down to number 20. All right, and then so what we're looking for here is that these are, if I don't have the graph, right? So all the ones that we had before, we actually had the picture of it on a graph and we could kind of see it, how it was moving. Here, we're just given some points. But so if we're doing a translation, and this says a translation of x minus 1 and y minus 4, well, what this means is that this means left 1, and left because it's negative, and then down 4 and down because it's negative. And then so left 1, down 4. So this, if I did left 1, so if I'm at 5, and you can maybe even, not that you have to do this, but I mean, if you wanted to, visualize this, you could kind of do a little sketch of it, 5 and then 2. So if I'm here, right, if I'm saying that's point F, and it says go left 1 and down 4, well, left 1, if I was at 5, and if I go left 1, now I'm at 4, and then I'm going to go down 4. So down 1, 2, 3, 4. So now I'm down here at -2. So that point right there would be 4, -2. Now you don't need to graph that. That's just one way to visualize it if you wanted to. Also, you could just subtract. Left 1 means take away 1 from 5, so 5 minus 1 is 4. Down 4 means take away 4 from 2, so 2 minus 4 is -2. So you didn't have to graph that. That's just a way to come up with a visual if you had wanted to. All right, so 21, same thing, no graph. We could always make our own graph. G is at 3, -4. So let's say 1, 2, 3, 1, 2, 3, 4, -4, that is. So here's G at 3, -4. And then what it's saying is that what if we do a reflection across the x-axis? Well, here's your x-axis. So if we flip it across the x, that means we're flipping up here. So you'll notice that the x value is going to stay exactly the same because all we're doing is we're just flipping up here. The only thing that's going to change is the y value because we're going from the bottom to the top. So 1, 2, 3, 4. So our point there would be 3, +4. And so in your toolkit, there's the rule, which is if you're reflecting over across the x-axis, the x value stays the same. It's just that the y value switches, and that is a -4, by the way. It didn't. Yeah, there you go. That is a -4. Next page. 22. So we've got a reflection across the x-axis. So we've got a reflection across the y-axis here. I think I'll do the same thing just to get a visual of it. Again, not that you have to graph it, but I think it's nice to get a visual. So -2, 5. So -2, 1, 2, 3, 4, and 5. So this is -2, 5, which is at point B, -2 and 5. And then it says we have a reflection across the y-axis. Well, the y-axis, again, this is our x and this is our y. So reflection across the y-axis means we're flipping it across the y. So we're flipping it over here. So what's going to change now is because the x value is changing. So the x value is now on the positive side over here. So this would be at a +2. And I could say B prime. And then, but notice what happened is the y value stayed exactly the same. The y value didn't change here. So the y value was 5, and so it's going to stay 5. So our B prime would be 2 and then comma 5. A rotation 23. So 23 and 24, we'll finish up this section on transformations. 23 is a rotation. We'll do the same thing. We'll just do a quick little sketch here to get a visual. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. A lot of us are visual learners, and the brain likes pictures. So on these ones where they don't give you a picture, make your own picture, right? Just sketch it out real quick. It doesn't have to be perfect. I'm not using graph paper. It's fine. We just want a quick little sketch. So what we want to do is now rotate this. So we're going to rotate the points. We're not flipping the point. We're not sliding the point. We're rotating the point. So, and 180 is going to be 2 turns. So we're going to do 2 turns. So if we do 2 turns, and remember we said that clockwise, counterclockwise, it's the same thing. So 1 turn would put us here, if I'm going clockwise, that is. And then a second turn from here would put us over here. So what that would be is now that point, it would be, now that it's in the 3rd quadrant, that x would be negative, so it'd be at a -5, and then the y, would also, because it's below the x-axis, would also be a negative. So my point here would be -5, -5. Last one, 24, at least last one for this section. We got a rotation in 90. So 90 degrees is one turn, and it's one turn counterclockwise. So one turn counterclockwise. So counterclockwise is opposite the way of the clock. So it's going to be one turn that direction. All right, well, let's see. R is at 4, 2. 1, 2, 3, 4. 1, 2. So R is at 4, 2. And we want to do one turn, and we want to do one turn counterclockwise. So if we were going in this case, and they kind of make my arrows consistent with what we're doing here. So I'm going to be going this direction. I'm going to be turning it this way. So clockwise would be going this way. Counterclock is one turn that way. So if I go one turn counterclockwise, that means I'm now in the second quadrant. And so what that means is that now I've got this one, I now have -2. And then this point is going to be, and again, my graph isn't entirely to scale, but what you'll notice is that now this ends up being a switch here. So this would end up being -2, 4. So again, consult your toolkit on this where you've got the rules. But basically what happens here is that the x and y values switch places. The y value stays the same. The x value switches. So again, you've got all those rules in your toolkit. Next section deals with slope and graphs. So this was a little review from Algebra 1. And so starting with number 25, we want to talk about slope. So on 25, let's say we've got, well, what is slope? Maybe we should start with that. So slope is just rate of change. It just is the steepness of a line. And how we measure steepness is we measure that by, and we use the letter m to represent slope, the change in y over the change in x. The little triangle is the Greek letter delta, and it just means change in. So it's just our little shorthand way for saying the change in something. And when we say the change in y, what we mean is how many did you go up or down? And then the change in x would be how many did you go to the left? Now, notice I didn't write left or right. I just wrote left. Reason being is because we always look at graphs from the left to the right, just like you read from left to right. If I went up, that number will be positive. If that number's, if I went down, that number is going to be negative. So looking at it from left to right, which means this point to this point, this is going downhill. Because you might argue, well, what if you started over here? Then isn't that going uphill? Yeah, if you started on the right, but again, we look at things from left to right. So don't start on the right. You're going to start on the left. And then I do my change in y first because the order of the fraction matters. Because there's a difference between saying 2 over 1 and 1 over 2. Those are two different numbers, right? There's a difference between $2 and then 50 cents. So the order of a fraction matters. So do the change in y part first, which means the up or down part first. So if to go from here to here, I'm going to go down 1, 2, 3. So that's going down 3. And then I'm going to count over 1, 2, 3, 4, 5, 6. So that would be right 6. And I'm sorry, I just realized I wrote left. I meant to write right. Oh, we've got to keep the colors consistent. Where's my red? There we go. Right. I was thinking we read the graph from left to right, but in terms of the movement here, because we're looking at it from left to right, we're counting how many steps did you go to the right. And that's always to the right. You're always looking at it to the right. Well, so the slope here would be my change in y would be 3, and my change in x would be 6. Notice that 3 over 6 is not one of the answers. Oh, and actually I just caught something here too. Notice I went down, right? So because I went down, I didn't go up 3. I went down 3. So that's down 3 and then right 6. So notice that -3 over 6 is not an answer. That's okay. I just need to reduce it. So what if I divided top and, let's see, what goes into both here? How about 3? What if I divided top and bottom by 3? Then I get -1 over 2, or -1/2. So that would be my slope. This line's going uphill, so I could already tell you that the slope's going to be positive. So I already can tell you that the answer is not going to be A and it's not going to be D. Let's count how many steps. So from this point to this point, how many up, how many over? It looks like we go up 2. That's up 2. And then right 1, 2, 3, 4, 5. So that's up 2 and then right 5. So up 2 and right 5. So I have a slope of 2 over 5. Notice they're trying to trick you. So notice B is 5 over 2. So the order does matter. So don't let them trick you on that. It's change in Y over the change in X. Now in 25 and 26, they gave us graphs to work with. If you look at number 27, what we notice here is that we don't have a graph to work with. So we're going to have to figure that out. Well, I could graph these 2 points, but they're also, it's kind of, I don't know, I don't have graph paper. And I mean, I could do like a quick little sketch here, right? Like I could think about what's happening here. -6, -5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. But here's the problem. So that's 1 point. But then the other point is -15. -15 would be way over here, and then a +5, which would be some point way up here. And then I'm trying to figure out like how many down and then how many over. Well, this is definitely going downhill. If I'm going from this point to this point, that's not a very good line, is it? So it's definitely going downhill. So I could already tell you the slope's going to be negative. So I know it's not A and I know it's not C. But then, I don't know, it's kind of hard to count that because I don't have graph paper. So what I want to do is that I'm going to try to figure this out algebraically. So what I'm going to do is I'm going to take these 2 points, -6, -5, and then -15, and then 5. And we said that the slope is change in Y over change in X, right? Change in Y over change in X. Well, what would be the change in Y? Well, to go from -5 to 5, what is that a change of? And when I say change, I'm thinking on a number line. If we had this number line and you're at -5 and you're going to +5, how many steps did you take? Well, you took 5 steps to get to 0, and then you took 5 more steps to get to 5. So that's a total of 10, right? That's a total of 10 steps. So my change in Y would be 10. And then what's my change in X? Well, from -6 to -5, or I'm sorry, -6 to -15, that's going down, right? So if I'm at 0 and I've got -6 and I'm going to -15, how many steps is it from -6 to -15? Well, that's going down 9 steps. So then my change in X here would be -9. And then so my slope is going to be 10 over -9. Now, you know, with a fraction, it's not that the top or bottom is negative. It's really just that the whole thing is negative. So how we would write that would be we'd put the negative out front, and then we would just say slope of -10 over 9. And that's what we get right there. There's a formula for this. There's a formula for, I prefer this approach. I think it's a little cleaner and you don't have to worry about a formula. There is a formula, which is y2 minus y1 over x2 minus x1. Which is basically the same thing I did here. I just did it without the formula and not getting tripped up with minuses and negatives and all that stuff. All right, so why are we introducing this why are we reviewing something from Algebra 1 here? Well, the point of it is that when we look at slope, if I have 2 lines that are parallel, and we know that lines that are parallel are lines that don't touch. The reason why they're parallel is because they're kind of going at the same angle. And if they're going at the same angle, that means they have the same slope. So any lines that are parallel have the same slope. So parallel lines have the same slope. The same slope. So if this has a slope of 2, and I know that the slope is 2 on this one, by the way, because it's y equals, y equals mx plus b. So in slope-intercept form, so the number that's in front of x, that's my slope. So the slope on this one, for instance, is 2. And so if the lines are parallel, then it's also going to have a slope of 2. What if it says, now this looks a little bit different. It says x equals 0. If I was to graph x equals 0, then x equals 0 is just going to be, well, it's right there at the origin. And then it's just a vertical line through the origin. And then so what's the slope of a vertical line? Well, we can ask our friend Slope Man. Slope Man, here's Slope Man real quick. If it's a line that's going uphill, that's a positive slope. If it's a line that's going downhill, that's a negative slope. If a line is completely flat, that means it has 0 slope. So that would be a 0 slope. And then if it's a vertical line, which this is, then we say that the slope is undefined because it doesn't have a slant because it's going straight up. So we say that the slope is undefined. So if this has a slope that's undefined, then anything parallel to it, right, which would be any other vertical line, either to the left or to the right, if it's vertical, then it's going to have a slope of undefined. Next page. So next one we're looking at is our slopes of perpendicular lines. So slope of a perpendicular line, perpendicular means they do touch, and they touch at a 90-degree angle. So let's say, for instance, that, and I'm just going to kind of sketch this graph. This has a slope of -2, and then it says it goes down 7, 2, 3, 4, 5, 6, 7, and then right 2. So it's going to be something that looks like this. Again, this is just a rough sketch. That's a rough line. I was trying to do my line tool. Here's my line. Ah, there you go. That's a better looking line. Now we're looking for the slope of something perpendicular to it. So something perpendicular would be a line that intersects, and I'm just going to, where they basically kind of form a cross, right? And then what we're looking for there is that they have, they form at a 90-degree angle. Now I just kind of, where I drew that blue line, I just kind of randomly picked that spot. But I just want you to see that what we're talking about here is we're talking about, they're perpendicular because this forms a 90-degree angle. And then so what we're looking for is what would the slope of this line be? Well, if the slope of the red line is -7/2, these don't have the same slope, right? Because the red's going downhill, the blue's going uphill. And they're also kind of going in a different direction. So what we say is that perpendicular lines have opposite reciprocal slopes. So opposite reciprocal slopes for perpendicular lines. So slope of a perpendicular line is going to have an opposite reciprocal slope. When we say opposite, we mean switch the sign. And then when we say reciprocal, we mean flip the fraction. So if the slope of this one is -7/2, and then I were to flip that, I'd have a positive 2/7 because I flipped the fraction and I switched the sign. So then that means this would have a slope, and that looks about right. If I went up 2 and then right 7, again, that was just kind of a rough sketch. All right, so that finishes up the section for slope. Next section we're going to look at is angle relationships that are formed by parallel lines. So starting here at number 31. So number 31. So identify each pair of angles as corresponding, alternate interior, same side interior, vertical, or adjacent. All right, well, there's a lot to say there. All right, so, well, basically what we're looking at is that you've got, and we're assuming, actually we're not given that they're parallel, but that's okay. So vertical, and this is again all in your toolkit, but angles that are across from each other, those angles are congruent. And if they are across from each other in this kind of X fashion, then we say those are vertical. Two angles that are, so these are not across, but they're next to each other, right? These two things are next to each other. So if two angles that are next to each other, adjacent means next to, just that word in general, right? I mean, you could say that, San Mateo and Burlingame are adjacent to one another, right? They're cities that are next to each other. So adjacent just means next to, right? And these aren't, and you guys say, well, aren't these next to? Well, no, these are across from each other, right? So they're not adjacent. These aren't 33, they're not adjacent, right? They're not next to each other. They are on the same side. If I look at these lines, and if I think about this as the inside, this is interior, and then this is exterior, right? If I think about like this is kind of like this sandwich, and then this is the inside of it. They're not on the same side. You notice that these are on different sides. So they're on opposite sides, or we also call that alternate sides. So that word alternate, we also kind of think of that is kind of on opposite sides. And I should mention too, I didn't mention this previously, but the name for this line that's cutting across, that's forming these angles, we call this the transversal. So that it depends upon how this line cuts across, it forms different types of angles. And so we have different names for those angles. Next relationship is what we'll call a corresponding angle. The reason why these are corresponding is because if you took your patty paper and you measured that angle and then you slid it down, you would see that it's exactly the same. So if I slid that angle down or up, I could slide that angle up. I see that they're exactly the same angle, just in different locations. And so we call those corresponding angles. And the last one on the page here, 35. These are on the same side, and they're on the interior, right? Remember we said this is the interior right here? And it's not alternate because they're not on. Alternate would be like if something was over here, like Y and Z would be alternate. So it's not alternate. And they're not in the same position. It's not corresponding because if I take this angle and I slide it up, it's not the same thing as this angle right here. These are two different angles. Hopefully you could see that, right? That this is more acute, and this is obtuse. That's a bigger angle. So they're not the same, and they're not across from each other. So because they're on the inside of the little sandwich and they're on the same side of the transversal, we call that same side interior. Next page. So now what we're going to use is we're going to use these relationships to solve. So what we know, and this is in the situation, notice now we have these red arrows. These indicate that these lines are parallel. So what happens? These are on opposite sides. So these are alternate interior, alternate, and again, all of these relationships and terms are in your toolkit. So these are alternate interior. So if this is 89, that means that also would be 89. So these angles would be congruent. So alternate interior angles are congruent. Again, that's this is our little symbol for congruent, which just means the same or equal to each other. Now 129, these angles are not congruent to each other, right? 129 looks much larger than our little mystery angle here. Think about a rectangle. If I had a rectangle, I know that this is 90 and this is 90, right? So these two would add up to, this total would add up to 180. Well, think of this as instead of it being straight, 90 plus 90 equals 180, think of this as being, think of it almost as a parallelogram. So think of this as leaning. And then so if this is 129, but the edge of it still adds up to 180, right? So this total thing is still 180. So we just have to find the difference between the two. So I just have to say 180 minus 129. And if we put that in a calculator, we'd get 51. So what we find is that same side interior equals 180. They sum up to 180. Now we're going to use these relationships to solve. So just a little more practice with our algebra. These are vertical angles, and we know that vertical angles are congruent. So vertical angles are congruent. So these are the same. 8x minus 1. And you can take your patty paper, and if you trace that, you'd see those are the same. So let's say 8x minus 1 is equal to 6x plus 13. And then so I just need to get my x's together on the same side. So I've got 2x minus 1. At this point, it's just a flashback to Algebra 1. So hopefully you're not struggling with that too much. And then divide by 2, x equals 7. And they're not asking me to substitute back in. Notice it just says solve for x. So all I need to do is just solve for x, and then there's my answer right there. Are these equal to each other? Again, no, look at it. This angle, if I look at that angle right there, that angle looks much smaller than this angle right here. So these are not congruent. I'm not going to set them equal to each other. What we did say over here is that same side interior equals to 180. These are the two corners of the box. It's just that the box is slanted. So, but the two corners are going to add up to 180. So what I would do is I would set this up as 8x plus 2 plus a negative 6 plus 15x equals 180. So these are same side interior. And we said same side interior equals 180. All right, well, let's just combine some like terms. I've got 8x and 15x I can combine, so that makes 23x. I've got a 2 and a negative 6 I can combine, so that makes negative 4. And then I just need to solve. So I'm going to add 4. So I get 23x. I'm going to write on top of my head. And then divide by 23. And x equals, come back. Where'd I go? There I am. 184 divided by 23, which would be 8. There we go. X equals 8. Number 40, moving down the page. Hang in there, we're almost there. Or more than halfway there. All right, so let's look at number 40. And so these two, they're not equal to each other. Again, you can always just kind of visually do a quick check. This angle is smaller than this angle. So they're not equal to each other. But what we do know is a linear pair, two angles that are on the same line, a linear pair, they're supplementary. They add up to 180. I also know that because if I try to make a circle here, that's half of a circle. And I know half a circle is equal to 180. So then all I'm going to do is I'm just going to say 50 plus x plus 139 plus 180. And then that's going to be equal to, I'm sorry, hold on. 2 parts, 50 plus the other part, x plus 139. That's going to be equal to 180. I think that's the thing you have to be careful with this one. It's just it's really easy to, you're trying to figure out, do I add them up to 180 or are they equal to each other? And so in this case, they add up to 180. Let's combine some like terms. So this would be 189 plus x equals 180. And then if I subtract 189, then I get x equals negative 9. X equals negative 9. All right, so those were all angles relationships, angle relationships formed by a transversal, a line that cuts across two other lines, and then the angle relationships that are formed there. Next section, we're going to look at angle relationships in a triangle. So next section is angle relationships in a triangle. So 41, we know that everything in a triangle adds up to 180. So the triangle, it's our Triangle Sum Theorem. Everything in a triangle, and again, this is in your toolkit. It doesn't matter what the triangle looks like, if this is A, B, and C. But what I do know is if I add up A, and I add up B, and I add up C, everything adds up to 180. So if something's missing, then I just need to subtract that from 180, right? So I'm just going to take 180, and then I'm going to subtract the two things I do know, which is 56 and 45. And then the difference is going to tell me what this angle is equal to. Use your calculator. Again, we don't want to make any silly little mistakes. So I'm going to do 180 minus, and then be careful here. Notice I used parentheses. So I'm going to use parentheses because I want the calculator to do what's inside the parentheses first, right? I wanted to add those two things together first and then subtract from 180. And so then I end up getting 79 degrees. 79 degrees. All right, what's my relationship here? Well, so I'll show you kind of the long way, then I'll show you the shortcut. So we know I want to find this angle, but to find that angle, I need to find what this angle is equal to. Maybe I'll just call that x, since they called that question mark. Well, let's find out what x is equal to. So I'm just going to do for this, I'm going to do 180 minus 90 plus 57. So let's do, and I also could type it in this way. I could just do 180 minus 90 minus 57, so I get 33. Now, 33 is not my answer. You notice that 33 is not one of the choices there. So this is 33 degrees. Now what they're asking for is they're asking for the angle that's outside of this. Well, again, I can see right away that this is a linear pair, which is half a circle, which is 180. So if this whole thing is 180, then I just got to do 180 minus 33 to find the difference, which is going to be 147. So this angle here is 147. Is there a shortcut? Yeah, there's a shortcut. So notice if you took 90, which is this angle, so if you took 90 plus 57, what's 90 plus 57? Well, it's equal to 147. So there's a little shortcut there, which is that the two angles on the inside add up to the one angle that's on the outside. But if you didn't remember that shortcut, that's okay, because you could just solve it the way that the way that I approached it on that one. All right, so let's look at the next page. All right, so we're going to use that relationship to solve for x. So we know that everything adds up to 180. So we're just going to say 85 plus 50 plus x plus 56 equals 180. So hopefully you see why being able to solve an equation is so important, because we use that in geometry to do a lot of different things. So let's combine our constants. 85 plus 50 plus 56, 91. So x plus 191 equals 180. And then I'm going to subtract 191. So I get x equals negative 11. I don't have to plug it back in or anything, so that's good enough. I can just leave it there. Now here's where the shortcut maybe kind of comes into play. So the shortcut that we saw back on number 42, where we take the two interior and add it up to the one that's on the outside. So here's where that shortcut comes into play, is that I'm going to take these two interior angles, which is 75 plus 8x plus 4, and that's going to be equal to 20x minus 5. I'm doing it this way. I could say that subtract these from 180, but then that would be kind of a longer way about it. So we're going to take advantage of the shortcut here. Let's combine some like terms. So 79 plus 8x equals 20x minus 5. Just get all your x's together on the same side. So 79 minus 12x equals negative 5. Let's subtract 79 from both sides. So negative 12x equals negative 84. And then divide both sides by negative 12. And we get x equals 7. So we're using this exterior angle theorem, exterior angle sum theorem, to use this as a shortcut. Exterior angle. And again, this is in your toolkit. So none of this stuff you have to know 100% off the top of your head. All this stuff's in your toolkit. All right, so we're going to use a couple more relationships with triangles. So let's scroll down here. 45. So these two marks right here, this indicates that these are congruent. And so if you have two sides that are congruent, then what we also find, well, first of all, we call that an isosceles triangle. Isosceles spell. We call that an isosceles triangle. And there's a relationship with an isosceles triangle, which is that if the sides are the same, which they are, then the base angles are the same as well. So what that means is that if this is 52, then that means that this is also 52 degrees, that angle right there would be 52 degrees. And then I can use that to figure out what x would be, because I know everything adds up to 180. So then I can just say that, well, x plus 52 equals 180. So let's combine that. So I've got x plus, and 52 would make 104. And then let's subtract 104. And then so I get x equals 76. Using that same relationship here again, it's a little different here. Instead of like putting the angle measure inside the diagram for me already, they're just kind of writing it here. But that's okay, because that's just the same thing, right? So all they're telling me is that is equal to x plus 81. So if that's equal to x plus 81, and we know that with an isosceles triangle that the base angles are congruent, so if that's x plus 81, then that means that this is also x plus 81. So then, and again, I know that everything in a triangle adds up to 180. So I've got x plus 81 plus x plus 81 plus, I can't forget about the angle here, right? I got to include that angle too. So because I've got a total of 3 angles, so I got to include that one as well, and that's going to be equal to 180. Let's clean some stuff up here. X and x makes 2x, and then let's combine all these like terms, 81, 81, and 40, and then let's just use a calculator on that. So 81 plus 40, we get 202. And then I'm subtract 202 from both sides. 202. And then so I get 2x equals 180 minus 202. 180 minus 202 is negative 22. And then I'm going to divide by 2. So I get x equals negative 11. So what we're looking for here with the triangle, and the next couple questions are going to refer to the Triangle Inequality Theorem. So if you're following along in your toolkit, you're looking for the section that says Triangle Inequality Theorem. And basically what it says is that two sides of a triangle have to be greater than the third side. So if you take 2, it has to be greater than the third. So like if I take 8 plus 9, and let's just say I call this, I don't know if I call this A, B, and C. So 8 plus 9, which is if I take A plus B, write it this way. So A plus B has to be greater than C. Well, is that true? 8 plus 9 is 17, so 17 is greater than 9. And then I have to try this for all 3. So then what if I said, well, A plus, let's just try a different one. Let's do A plus C. Is A plus C greater than B? Well, A and C is also 17, and then which is greater than 9. And then I haven't tried B plus C. So B plus C has to be greater than A. So B plus C is greater than A. Is that true? So B plus C is 18, right? 9 plus 9. So 18 is greater than 8. So in all of these cases, so again, two sides have to be greater than the third. And this is true for all of these. So then this would make a triangle. Let's do the same thing here. I'll call this A, B, and C. Let me do A plus B greater than C. Is this true? Is 16 plus 11, which is 27. 27 is greater than 5, so that's true. But I have to try it for all 3. Let's do A plus C. So A plus C, is that greater than B? Well, A plus C is 21. 21 is greater than 5. How about B plus C? So let's do B plus C. Is that greater than A? Well, B plus C is 16. 16 is not greater than 16. 16 is equal to 16, but 16 is not greater than 16. So that is false. And so if I have one of the 3 that's false, then the answer would be no. Now, if I'm not given all 3 sides, let's say that I'm just given 2 sides, and then what I'm trying to figure out is that what could that third side be equal to? Let me push this up a little bit. So an extension of the Triangle Inequality Theorem is what it says that if you take and again, this is in your toolkit, but if you take the the biggest side. So we're going to have some number here. And what we're looking for is this is going to be the sum of two sides. And this is going to be the difference of two sides. And it's the difference of the two sides they give us. So what I would do with this is that the difference of the two, if I subtract 47 minus 31, I get 16, right? Because that would be 47 minus 31. And then the biggest side would be the sum of the two sides, so 47 plus 31, which would be 78. And then what that does is it tells me how small the third side could be and how big the third side could be. Because what we don't want to happen with a triangle, it's not a triangle if they don't quite meet, then it's not a triangle, right? Because if it's too short or if it's too long, then so what we're saying is that what's the smallest it could be and what's the biggest it could be that they would meet. So less than 16 they don't touch, and then more than 78 it hangs over. So our answer there would be B. All right, so number 50, starting with number 50, this deals within our Pythagorean theorem. So we know that Pythagorean theorem is a squared plus b squared equals c squared. You could also write this the other way. You could also write it as c squared equals a squared plus b squared. I prefer looking at it this way because we're going to use this, viewing it this way, we're going to use it to answer a question coming up. But let's deal with this one. So what do we, and again, in your toolkit, two legs, this would be A, that would be B, and then this would be C. C is always the hypotenuse. It's always the side opposite the right angle. So we call that the hypotenuse. I'll just abbreviate that as HYP. And then A and B, and it doesn't matter if I call that A and B or B then A. You just got to get the hypotenuse straight. And then what this does, so A is a leg, B is a leg, and then C is the hypotenuse. And then what we're going to do is we're just going to fill this in. So C, I don't know what C is, so I'm just going to leave C as C squared. A is 56. B is 42. And then what I'm going to do is I'm going to take 56 squared, which is, go away. So 56 squared, again, use your calculator on this one. 56 squared would be 3,136. 136 plus 42 squared. 42 squared is 1,764. And then we just need to add those two things together. So plus 3,136, which would be 4,900. And then we're just going to take the square root of both sides. So we're going to take square root. Why am I taking the square root, by the way? Well, I want to get C by itself, and I got to get rid of that little 2. That little 2 means it's being squared. So, in algebra, we always do the opposite to get rid of things. So the opposite of squaring something is to take the square root. It's kind of like those two things cancel each other out. And then what you're left with is just C. And then what I do to one side, I have to do to the other side. So I need to take 4,900, and then I'm just going to take the square root of that, which would be 70. And so my answer there would be B, which would be 70 inches. Next page. Here's another Pythagorean theorem question. So let's do c squared equals a squared plus b squared. Label your legs. So I could call this is a leg, this is a leg, and then side opposite the right angle, that's always my hypotenuse. So my hypotenuse in this case is, I know what it is, it's 60. So I've got 60 squared equals a squared. And again, it doesn't matter if I call a x or 48, same difference. So I'll just say that's x squared and then plus 48 squared. And again, we're going to use our calculator here. So 60 squared, 60 times 60 is 3,600. 3,600 equals x squared, and then 48 squared, 48 times 48, which would be 2,304. 2,304 minus 2,304. So 3,600 minus 2304, and so I get 1296 equals 1296. And then let's take the square root of that. So square root of 1296, and I get 36. I get 36 feet. All right, next section, we're going to use the relationship with the Pythagorean theorem to figure out whether a triangle is right, acute, or obtuse. So the relationship, and again, this is in your toolkit, but how it ends up being is that if the largest side squared is equal, and just because this looks like a right triangle, I can't assume that that's a right triangle. So I actually have to test this out to see if that's true. Now, what ends up happening is that if the square of the larger side is less than the sum of the other two, then we would say that that triangle is going to be acute, which means that it would be smaller. And then what happens is that if the larger side is squared is greater than the sum of the other two sides, then this would be obtuse. So let's test it out. Let's take the largest side, which in this case would be 60. So I'd have 60 squared. And I'm just going to write question mark because I don't know if it's equal, less than, or if it's, I'm sorry, I wrote equals here. Let me clean that up a little bit. So this would be a greater than. So I don't know if it's less than, equal to, or greater than. So I'm just going to write a little question mark there. And then I'm going to take the other two sides. So this would be 41 squared plus 48 squared. And then what I'm trying to do is I'm just trying to test this out. So 3600 and then 41 squared. So let's do 41 times 41. So I get 1681. And then let's do 48 squared times 48, which would be 2304. 2304. And again, I don't know if these are equal to, less than, or greater than. So let me add these two. So 1681 plus 2304. And I get 3985. Well, those two numbers are not equal to each other, so it's not a right triangle. 3600 is less than 3985. So if it's less than, then that would be acute. Let's try this one over here. So take the largest side, which is 45. So 45 squared plus, I'm sorry, 45 squared question mark. And remember, C is the longest side, right? So this is, remember, the thing here to remember is that C is the longest side. So when you're setting this up and you're looking at the numbers, how do you know which one is the C? The C is always the longest side. So 60 was the longest. And this one, my C would be 45. And then so let's take 40 squared plus 9 squared. Again, we'll use a calculator here. So 45 times 45, so we get 2025. 2025 question mark. 40 squared would be 1600 plus 81. So 1600 plus 81. The 1681 to 2025 is greater than 1681. So that means that that triangle would be obtuse. All right, so next section deals with looking at similar triangles. But to be able to do that, what we need to be able to do is we need to be able to solve proportions. So if we look at proportions, a proportion is just a situation where you have two fractions equal to each other, right? And then so our method for solving in this kind of situation is that we're just going to cross multiply. So I'm going to cross multiply this direction. So if I cross multiply that direction, that would be 4 times a minus 12. And then if I cross multiply, excuse me, this direction, then that would be 3 times a plus 12. And then because you see the equal sign there, they're equal to each other. So there's a couple different ways you can annotate this. Sometimes people, circle these two things or draw arrows or however you want to do that. But annotate that in some way so that you remind yourself of what you're doing there. And then we're just going to solve for the equation here, right? So we just got to distribute. In this case, we're going to solve for A. So 4A minus 48 equals 3A plus 36. And then I'm going to subtract. And so I get A, 1A or just A, minus 48 equals 36. And then I'm going to add 48. And then, so 36 plus 48. Where'd my calculator go? There it is, 36 plus 48. So we get 84. So A is equal to 84. All right. Now we use proportions, and they're going to come into play here in a second because we're looking at dilations. Dilations are a situation where you change the size of a shape. You either enlarge it or you shrink it down. So if I look at 55, what we're saying is there's been a dilation of 0.25. So dilation of 0.25, and we use the letter K to represent what we call our scale factor. That's just the amount that you are changing the size by. So if K equals 1, then the shape stays the same. It didn't, if we just multiply, right? Because 1 times anything is just itself. But what happens is that if we multiply, let me move this. Look at it. This is fancy. If we multiply by something greater than 1, so let's say K is greater than 1, then it's an enlargement. What we're doing is we're making the shape larger. And then if we multiply by if we multiply for anywhere from between 0 and 1, then it's a reduction. We're making it smaller. So 0.25 is less than 1, so this is a reduction, so we're making it smaller. All you have to do is just multiply each number by the scale factor. So I would multiply, to get f prime, I would multiply 3 times 0.25, and then I would multiply 1 by 0.25, and then that would tell me what the new coordinate would be. So 3 times 0.25, and again, just use your calculator on this one. 3 times 0.25 would be 0.75. And then 1 times anything is just itself, so 0.25 times 1 would just be 0.25. And so that gives me the reduction. If K was, if we were doing a dilation of greater than 1, then I would just multiply whatever the number is, that's what you'd multiply each X and Y value by. So this is where we use then these proportions. Is what we want to do is when you say that they're similar, what we mean here is that they're the same shape, just different size. So one's smaller, one's larger, but they're still the same shape, which in this case would be triangles. So they're both triangles. It's just one's bigger, one's smaller. So what we have to do is we have to then match up the sides here. So what I'm going to do is that I'm going to match up the smallest side to the smallest side, and then the biggest side to the biggest side. And so if I did match these up, then the smallest side here is 36. And let me use my highlighter here. Right, so I'm going to take this side, which is 36, and then I'm going to match that up. And we're solving for X in this case. So let's see, that would be 42. So we're matching up these sides, and then we're matching up these sides. And what you can kind of think of what happened here is that these two triangles, there was a rotation. So not only did we change the size of the triangle, but we also rotated the triangle as well. So I'm going to match up the two sides that match up here. And sometimes it's tricky to tell what exactly happened to the triangle. 36 matches up with 10x plus 2. And then that's going to be equal to, and then 48 is going to match up with 56. So 48 would match up with 56. And then here's my proportion. So I'm just going to cross multiply. So I'm going to cross multiply this way, and then I'm going to cross multiply that way. So 36 times 56, and I'll go ahead and write this out just so you see where this is coming from. And then I've got 48 times 10x plus 2. So 36 times 56, 36 times 56 is 2016. And then 48 times 10, 48 times 10 would be 480. So 480x. And then 48 times 2, which is 96. And then I'm going to subtract 96 from both sides. So 216 or 2016 minus 96, and I get 1920. Again, use your calculator on all this so you don't make any mistakes. And then divide by 480, and so I get x equals 1920 divided by 480, and so I get 4. So x equals 4. So x equals 4. So we're going to do the same thing here. So we're going to match up, which side would match up with which here. So 78 is, and it looks like in this case that this would be an isosceles triangle, right? Because these two sides are the same. So what we're going to match up here then is that I could kind of, there's really kind of a shortcut I could take advantage of here, which is that if these are the same, then these are the same. So if this is equal to 91, this is going to be equal to 91. And then so I could solve it. I could just say 17x. So let me show you kind of two ways of looking at this one. If these are, so this is isosceles, right? So this is going to be, these two are the same, which means that these two are the same. So if these two are the same, then 17x plus 6 is equal to 91. And this is, me setting it up this way is only because they're isosceles. This is the only reason why I'm able to get away with this. Not all of them are necessarily going to be isosceles. So this would not work in every situation. 85, but I'll go ahead and take advantage of it here. So x equals 5. Now, what if they weren't isosceles, or what if you didn't recognize they were isosceles? Well, you would just you'd set it up the same way that we did in number 56, which is that you're just going to match up your corresponding sides. So let's say that 78 matches up with 91, and then this side over here, 78 is going to match up with 17x plus 6. So what we would do, we'd set these up. So let's say 78 matches up with 91. And then 78 matches up with 17x plus 6. And then, again, I'm just going to cross multiply here. Anytime you have a proportion, you're just cross multiplying. So I'm going to say 78 times 17x plus 6. And then 91 times 78. And then if you solved all of that out, because we already kind of know what the answer there is, I showed you how to set it up. But yeah, so if you solved all that out, you'd get x equals 5. All right, now we use this relationship to test whether triangles are similar or not. In 56 and 57, we were given they were similar, but we may not always know that up front. We may have to test that out. So one thing that we do is we look for the same scale factor. So we're going to ask ourselves here, do all corresponding sides have the same scale factor? Same scale factor. For all corresponding sides. And this is because if we're given 3 sides, so we call this side, side, side. But what we're asking here is that do they? Because we don't know for a fact if they do or not. So what we have to do is we have to match up the sides. So we're going to match up smallest with smallest. So the smallest in this one is 28. And so 28 would match up with the smallest on this side, which would be 77. And then we'll match up the middle one. So the middle one here is 31. Middle one here is 88. And then we'll match up the largest one. Largest one here is 40. Largest one here is 110. What we're looking for is we're looking to see if they all have the same scale factor. So let's say I match up. So I do 28 over 77. And then I've got 31 over 88. And then I've got 40 over 110. Now, I don't know if these are the same or not, so I'm just going to use the calculator and simplify that. So I'm going to do 28 divided by 77. I'm just going to put this into a decimal. So I get this is 0.36 repeating. And then I'm going to do 31 divided by 88, which is 0.352. So right away, I could see that these don't have the same scale factor because these are definite decimals. But I'll just go ahead and check this last one as well. 40 divided by 110, which is 0.36 repeating. So the first two, or I'm sorry, the first and the last one do have the same scale factor, but this one doesn't. So this would, what we'd say here is not similar. Now, if they all had the same scale factor, then this would be the answer. But since they don't, if all same scale factor. That would be the answer. But they don't, so then it's not similar. Don't have same scale factor. Okay. Now notice on this one, they don't give you all three sides. They give you two sides and an angle. So when you have a combo, so this is, you have an angle there. Those are vertical angles. So now what I'm checking for is not, I don't need, and this is our side angle side situation, which is that if two of the pairs of sides have a same scale factor and an angle in between them, then we would say that those are similar. So we just have to check for two scale factors here. So let me identify matching sides here. So I'm going to match up if I take in this one, if I take the smaller one, so 18 matches up with 24, and for this one, 39 matches up with 52. And so what I'm checking for again is I'm checking to see if they have the same scale factor. So I'm going to say 18 divided by 24, and then I'm going to say 39 divided by 52. I'm just going to simplify that to a decimal so I can compare them. So 18 divided by 24, I get 0.75. 39 divided by 52, I get 0.75. So I do have the same scale factor here. So since these are the same, those equal each other. This was not equal to each other. So since these equal each other, I do have the same scale factor. So I would say that these are similar by side angle side. Why is it not side, side, side? Well, because I don't have three sides. I only have two pairs of sides, but I've got an angle in between them. All right, so let's finish up kind of our last relationships here. 60. So if I take a look at this one, on 60, again, this is where you're looking for if they all have the same scale factor. So match up the corresponding sides on this. And then what you're going to find is that, again, match up the small with the small. So like I would match up 35 with 98, and then match up 55 with 153, and then match up 64 with 182. And then what you're going to find is that when we check for the scale factors here, so 64 divided by 182, 55 divided by 153, and then 35 divided by 98. Again, just put that into a calculator to check for the scale factors. 64 divided by 182 is 0.35. 55 divided by 153 is 0.359. Maybe we should have went to another decimal place there. And then 35 divided by 98 is 0.357. And let me go back to what 64 divided by 182 was. Go to another decimal place. 0.351. So notice that these are all different. And so what we'd say there is this would be not similar. Notice this one, they don't give you any of the sides, but they do give you two angles. They give you one angle given here, angle U and angle C. And then we know that vertical angles are congruent, so I can mark those. And then what happens is that if I just have two of the angles, that's good enough. And so that's called angle-angle similarity. So that's enough for me to say that those two are congruent. And then the last ones we'll look at here, 62 and 63. So we're just looking at, are all the angles congruent here? 79 and 38, 77, 40. Well, let's say I can already tell you that these two, you'd need two of the angles, and these angles aren't the same. Even if I found the third missing angle, let's say I did 180 minus 79 minus 38, that would be 63. And then if I did 180 minus 77 minus 40, that would be 63. So they have one angle that's the same, but that's not enough. I need at least two of the angles to show similarity. And so in this case, that would be not similar. And then the last one here, this is a combo situation. I'm wondering if this is an SAS situation. But for this to be true, I've got the angle the same, but these scale factors have to be the same. So let me double check the scale factors here. So the small matches up with small. So 7 would match up to 16. The bigger matches up with the bigger, 13 and 24. Let's check scale factors here. So I would have 7 over 13, and then I've got 16 over 24. And then let's check that with the calculator. And we just want to see if we've got the same scale factor or not. 7 divided by 16, which would be 0.43. 0.75, and then 16 divided by 24, 0.6 repeating. So that is not the same scale factor. There's stuff on my screen here. So these are not equal to each other. So we would say these are not similar. All right. Well, thanks for hanging in there. I know that was a long one, but we want to make sure that you're ready for this final and that you are comfortable with all the material that's on it. So this concludes the video. Stay safe, stay healthy. We'll see you next time.